All right, everybody, welcome. As you can see, my setup was extremely involved.
Don't start yet.
Oh, okay.
Sorry.
Denied.
Normally at DEF CON, they make him do a shot. But this isn't DEF CON, this is B-Sides Pittsburgh. So instead, we make all our speakers wear blinky cat ears. Pull out the little tab, and there you go. And then push the button.
Gotcha. All right, yeah, hey, how do I look? All right. So yeah, you guys saw me fumbling with everything in my bag, that feeling you get when your Flipper Zero is on the bottom of the bag under everything else. So I brought a ton of stuff thinking, oh yeah, I could do all these demos, it's gonna be wonderful. We are surrounded by steel and concrete, so all my demos are probably not going to work, but that's okay, some of them I got videos for, but I'm still gonna go through the motions, you can see how this stuff works. So yeah, let's do this. All right. So I am going to introduce you to software-defined radio. This is applied, meaning that I'm not going to go through much of the theory. I'm going to talk about mostly what you would use software-defined radio for if you were a beginner, intermediate, maybe some advanced stuff. But I'm giving it a little bit of a flavor. I'm giving it some of that offensive and defensive flavor. This is all material that I've been able to accumulate from maybe 12 years of doing this stuff out in the field. A lot of the equipment that I had was very plug and play, advanced equipment, and if you tried to dig into it, it would be very complicated. So instead, I'm using stuff you can get on the market. Some of it costs maybe 20 bucks. Other things are a lot more expensive than that. But I just want to show you what you're capable of doing with just some basic software-defined radio and not a whole lot of skills. So this is not going to be comprehensive by any means. There are some of you in there that probably know a whole lot more than I do when it comes to using this equipment and applying it to certain situations, but that's okay, because there are some people in here that probably have no experience, and that's great. If you take something away from here, that's fantastic. To me, that's comprehensive enough. I'm not going to get that complicated for reasons I already explained, because a lot of this stuff may not work, especially when you're looking at aircraft signals, stuff like that, just because the signal's not going to be able to penetrate the structure. It's as simple as that. Radio is very finicky. And then it's not going to be exact. When you key a frequency into a radio, depending on the quality of the radio, you may get that frequency, or you may get something that's a few hertz or megahertz over that way or over that way. It's not an exact science. Radio is fluid, radio is weird, but it's a whole lot of fun. So who am I? I'm former Air Force, I just retired. I dealt mostly with signals intelligence. I did a lot of language translation, some language mistranslation. I did a lot of digital network intelligence stuff, which is fine and good. It's very complicated, but delving into that realm, it kind of got me into, well, this is all great. It's all OSI, model layer 3, maybe some layer 2, layer 4. That's great. Everybody was ignoring the layer 1. It's like as soon as the Cold War ended and we got into the global war on terror, everything was about cyber, cyber this, cyber that. People kind of forgot about what's going on in the airwaves. There's a process we use called electronic preparation of the battle space. That's where you go in with weird equipment like this, you see what's in the airwaves, and you try to decipher what it is, you try to assign it to a particular target. If it's not your target, you ignore it. If it is your target, then you assign it to somebody and they analyze it. Without that kind of preparation, you're just going to be flying blind. You have no idea what's in your environment. You have no idea how the adversary is communicating. You have no idea if the way that you're communicating is going to work, because it might be interfering with something that's already in the environment. So I also did a little bit of forensics. I do some penetration testing. I'm not going to get into that. I really like radio. I say that I'm obsessed with RF. I like it because a lot of other people don't. So it's a very accessible hobby, but it's also a way that you can try to manipulate your environment just a little bit. Your Wi-Fi's not working? Great. I know how to survey that to see what's interfering with it so you get the best signal. You get interference on your TV, it's all staticky because you haven't joined the 90s and you have rabbit ear antennas like these for your TV, fine. I can show you how to orient that to get way better TV signal. In fact, I will take you to the store and buy you a digital antenna. I will do you that solid. I also like long walks on the sidewalk. I'm not a beach guy. I've never been a beach guy. You can tell from my complexion I'm a vampire. If we had to do this shirtless, I would blind all of you with how not tanned I am. So let's move on. SDR is just what it sounds like. It's software-defined radio. Your typical radio, it is going to have a few circuits, a few crystals. It might have some coils of copper. It's going to have something that moves along those coils of copper, and that's what's going to resonate on certain frequencies. It's a radio. Who here has not built a radio? Or who here has built a radio? It's kind of a dying art. Yeah, a lot of you. That's awesome. Software-defined radio is taking all that and turning it into binary. It's radio on a chip. Essentially, what you're looking at is something really small, compact, that has a little bit of circuitry in it, and that circuitry has one job. It converts electrical and electronic signals into something that a computer or a software application can read. So electrical signal, radio signal, into binary. Binary back into electrical signal, that's all. What it's missing is what a radio like this has. It's missing a display, it's missing speakers, it's missing something to modulate or demodulate certain signals. It's missing something that allows a human to understand what these antennas are picking up. So with a software-defined radio, you have kind of the radio, but then you need the software to define it. And that's where your laptop, your computer, your Raspberry Pi comes in. The antennas are going to do what antennas do. They antenna. So when you're using a software-defined radio, think of it as the computer and the SDR module itself are the radio. The antenna means something. It's just like any other radio. You need the right antenna to do the right job, and we'll get into some of that. It's very versatile, extremely versatile. You could do everything from talk to satellites to hack Wi-Fi and hack somebody's car with a software-defined radio. In the old days, you used to have like very specific equipment that would have to do this. You have one tool for the job. Anyone here clone cards? You use a Proxmark 3 to clone cards, and you can get into hotel rooms. We're not going to get into that either, but it's been done. You need to clone a key fob? Great. You have a sub-GHz receiver. You can do that. With a software-defined radio, with the right stack, with the right equipment built up on it, with the right application, you can make one SDR module do all of that stuff. It's a lot less crap you got to carry in your backpack. So that's what that comes down to. And you can see from the pictures, there's a lot of applications. This can be for satellites. It could be as big or small as you want. You can have your cell phone do it. You can have a Raspberry Pi do it. You can have an Arduino do it. Everything that can run signals and run an application can do SDR. So this is what I'm going to introduce you to today. You have a Flipper Zero. I don't think anyone knows what these are. You have a Hack RF. Hack RFs are fantastic. And then I also have an RTL SDR. Here are some of the key differences. An RTL SDR is it's affordable, it's versatile, it's nice, it runs really hot, so don't touch it after you've been using it for a half hour, but it's receive only. A Hack RF can do all the stuff that an RTL SDR can do, but can also send signals, and that's going to be important for some of the stuff we get into. And then a Flipper Zero can do all that. It can receive, it can send, but it's like a Swiss Army knife. Has anyone here ever tried to build a shelter just with a Swiss Army knife? It sucks. You're using the right tool for the job, but it's not the right size and configuration of the tool. You can do a lot of stuff with a Swiss Army knife, but not all of it is good. You'd rather have a real corkscrew instead of the corkscrew on the Swiss Army knife. That's a Flipper Zero. It can do a lot of stuff, but there are better tools out there that can do the same stuff it can do. But if you want something that's just in your pocket that may or may not get confiscated at the Canadian border, that's a Flipper Zero. All right. Some of the software we're going to be using. I have a couple of favorites. I like SDR Sharp. It's made for Windows, but it can run on Linux. I also like SDR Angel. It's made for Linux, but it can run on Windows. And if it can run on Linux, it can run on Mac. So for those Mac users out here, you can more than likely use the same stuff I'm using. If not, a very cursory Google search will give you a whole list of SDR applications that you can use, that you can pair with your hardware, that'll do all the same stuff that I'm going to demo today. Just a couple of definitions here. When I say noise floor, what I mean is you have noise, and then you have nothing. If you're listening down here, you're going to get all the noise. You're going to get static, voice, digital, whatever it is. If you listen above that, you get nothing. That's your noise floor. You can raise it or you can lower it depending on your sensitivity level. A peak. When you key a signal or you try to hone in on a signal, that signal is going to peak up. And you can tell the noise floor is going to raise where that frequency is. That means there's something interesting there. When you start getting good at this stuff, you can tell what kind of signal it is just by what the peak looks like. And then you have the waterfall. The waterfall is the multicolor thing underneath that histogram. It is going to flow steadily down this way, and it's temporally engaged, meaning that if you find a peak or some other change in a noise floor, it's going to change the color of the waterfall where that peak is. And if that peak goes away, you'll see in the waterfall that color change goes away too. It's kind of cool. It's real time. If you record it and you leave a radio just sitting somewhere for a few hours, you can go back and you can review the waterfall and you can see where there were peaks, where there were changes in color, what frequencies are present in this area. You're doing your electronic preparation of the battle space. You are seeing the frequencies that are present. All right. The first demo is going to be with just plain FM radio. This is a Baofeng radio. You can get this on Amazon for like 100 of them for 5 cents. Like they're really, really cheap. They also break a lot. So if you can get a 10-pack, I recommend that. When the apocalypse comes, you'll be ready. It's either that or you spend $400 on that really, really good Kenwood radio that can do everything. But the problem is that Kenwood is made for amateur radio, only the ham bands. This guy can go on MURS, FRS, GMRS, maritime, airband, FM radio. It can do all kinds of other stuff. It's not restricted by the FCC. What that also means is if you mess around with this, you're liable to get yourself slapped on the wrist somehow by the government. So be careful with something that's like this. If you just want to listen to stuff, you're fine. It's transmitting that's going to get the cops called after you. Please ask me how I know. All right. So the first thing I'm going to do here is I'm going to call up SDR sharp. I am keyed to 462.612. That is the frequency I'm on. I'm going to change this to 462.612. You guys can only see the slides. Let me end the show. We'll start it back up when we need to. Come on, man, the live demo gods are not being nice to me. All right. There we go, good. So I'm at 462.612 on the radio, 462.612 on SDR sharp. And this is reading the signal that's coming into these rabbit ears going into my RTL SDR. If you recall, that's the small gray one that's receive only. Here we go, I'm going to key it. And that's what it looks like. If you had a good, expensive Kenwood radio, you would see one peak, and it would look so nice. This is a $30 Baofeng. It is not going to be a clean signal, but it works. It definitely works. Here, I'll even test it out. Check, 1, 2, check, 1, 2. I wonder if you guys were able to hear any of that. Probably not, but that's okay. Check, 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 check. That's all right. It's an imperfect system, but this is what you would set up, and you can set up however many number of these with any number of antennas on any number of frequencies to try to get an idea of what's playing in your environment. My local Chick-fil-A uses channel 20 on GMRS to convey all of the orders. So I tune this to what channel 20 is on GMRS, which is 462.612, or something close to that. So I can hear it when they radio my order in. So if they get it wrong, I already know what's up. You can do this. In a more military sense, if you are trying to radio for enemy activity, you can set up an SDR or something similar to this to have a very wide range and a wide band of receive. And you don't have to listen to the communications. You just look at the waterfall while the waterfall is going down. And if you noticed, when I keyed, there was a waterfall change. You see that? If I recorded that waterfall and I played it back at like 10 times speed, 20 times speed, whatever, and I paused it whenever I saw a change in the waterfall, I can snapshot that, see where the frequencies were, and then if I was recording everything that this was pulling in, including the audio, then I can go and analyze the signal. Is it data? Is it voice? Is it visual? Is it graphic? Is it analog? Is it packet radio? After a while, you can tell by what the peaks look like for what kind of digital data it is, or analog data. Make sense? All right. Let's get back to my slideshow, because you guys love slides, just like I do. All right, so we demoed that. The next thing that I wanted to demo was ADS-B signal capture. ADS-B, it breaks out to something nobody cares, but essentially it's similar to transponder frequencies that come off of aircraft. When you pick up these signals, you will be able to see the aircraft call sign, its altitude, its speed, its direction, and if it has any information about its destination and where it came from, its point of origin, you'll see that too. You can see the make and model of the aircraft, and if you're savvy enough with ADS-B, you can actually plot its coordinates on a map so you can see what's going on. This antenna over here is an antenna that is specifically designed for 1090 megahertz or 1.09 gigahertz. It is specifically designed to pick up ADS-B signals. I tested it out in 4 different places in this convention center, and the only place where I can get live signals was at track 1. So they put me in track 2. So I'm not going to be able to pick up anything live, but I made a recording of some of the stuff that I picked up, so we can possibly watch some of that. Right. So you can see that the aircraft are moving. You can see that I'm selecting some of them to see what kind of aircraft it is. We have one that's southbound that I have selected. We have another one that's going eastbound. This one is East Coast Jets. It's a Learjet, which is nice. This one over here is a Boeing. You can see that it's going to Detroit, Philadelphia, Detroit. This one is out of LaGuardia. And these are live almost real time. You can see the altitude, you can see their squawk, you can see what kind of plane it is, the heading. You could zoom in and you could see some more detail if you wanted to. You can see that you have an X on the ground where you'd be able to see it from directly up. And then those vertical lines to the icon of the plane, that's kind of representative of its altitude. You have people that have these things set up all over the world. All you need to do is just look for it online and you'll see these live feeds. This is another way that somebody that didn't have special equipment could set up via some air tasking order how we can detect the air traffic in a particular area if we wanted to do an operation. Is there going to be interference in the air? At what altitude? Is it commercial? Is it private? Is it mostly helicopter? Is it twin engine? Is it 4-engine? What is it? And this is a good way to do that. ADS-B signals are unclassified. You can pick them up wherever. The program I'm using is called Dump 1090. I'm not a fan of the name, but Dump 1090. It dumps all of the packets I'm capturing at 1090 megahertz, and it gives you all of this digitally. Having a server give it to you on a map is a good, nice to have. And that's something that makes it look pretty. But in reality, if you're going low power and you don't have an internet connection to manifest a map like this, just this text over here is good enough to give you all the information that you need. All right. We already did this. I would like to go past this now. All right. If you don't have this equipment, like I said, you use someone else's. Here's a few websites where you can go where you can see some of these live feeds. You can pick the location and you can see whatever aircraft are flying. Some in-laws are coming to visit and you want to track their aircraft. If it took off in time, yeah, you can go to Delta's website or whatever. Or, and bear with me on this one, you go to one of these sites near their airport, see if anyone is tracking the ADS-B activity, and then you can tell them exactly when their aircraft took off, what path it's taking, and you could even be their tour guide. You could track it for the entire trip. If you have a map behind you, you can tell them, hey, you guys, just so you know, at this time you were passing by whatever. If you look down to your left, you could have seen this lake. It'll amaze them. And that's ADS-B. So let's get a little bit deeper into this now. Those are pretty good beginner projects. That'll probably keep you entertained for a month or so. Then you want to start getting a little bit malicious. I like messing with sub-GHz. Sub-GHz is anything that's below maybe the 2.4 gigahertz Wi-Fi range in the ISM band. Now you're looking into things like IoT, car fobs, key fobs, home alarm systems, industrial controls, PLCs, stuff like that. I like to mess with these things because I like to tell people, hey, I messed with it. This is how you could fix it. It's kind of my job. So that's why I like to mess with this stuff. But with software-defined radio, you can detect all kinds of signals. The real challenge comes with, well, what signal is it? Because we are immersed with RF these days. There's sub-gigahertz stuff everywhere. You walk around your house with a spectrum analyzer, you'll pick up dozens and dozens of signals and be like, where the hell is this stuff coming from? What is this? You could have a smart device that you don't even know about. It could be the tire pressure sensor monitors on your car that are keying at 430 whatever megahertz. It could be your alarm system. It could be your door alarm. It could be a camera. It could be decked cordless wireless phones. It could be a baby monitor. There's so many things that it could be. A lot of the fun is investigating it, but if you dig too deep, it'll also frustrate you. But that's neither here nor there. What I'm going to get into is trying to hack some of this stuff. This is my disclaimer. If you want to do any of this stuff, you're going to do it with your own equipment in a home lab, or you're going to do it with somebody's permission. Do not be stupid with this kind of stuff. Homeland Security, the FBI, and the FCC, believe it or not, they have enough teeth that if you mess with some electrical grid or some other IoT or commercial alarms, they will come after you. So what I'm going to demo is going to be that kind of stuff, but it's going to be low power, and it's not going to mess with anything. If anyone here suddenly has lapses in like some device or some service or whatever, I'm sorry. I'm sorry, but you chose to sit here, so let's move on. All right. Your typical order of operations for signal analysis is you pick up the device. If it is made in the US, particularly, you look for the FCC ID. The FCC ID is something that you could find online. You go to fccid.gov, something like that. You can do a cursory Google search. It'll take you right there. You pop in that alphanumeric FCC ID. It'll take you to a spec sheet. That spec sheet will say what frequency it operates on, and then bam, you have a starting point. And this is if you want to analyze some device like your car key fob or something else that you happen to buy in the US. If you want to go even deeper, you can demodulate the signal to see exactly what the binary says, because sometimes it's not just an on-off signal. Sometimes it carries some data, maybe like a sequence counter or, some other random number generator like for a key car fob or a car key fob. Sometimes it is that simple. Other times it really isn't that simple at all, and it takes a lot of work to figure out exactly what you're looking at. I wanted to test this device. This is an alarm. It's something you could put on a door, a cabinet, a garage door, anything. The way that it works is that you have the alarm unit, and then you have this mag strip over here. When they are matched up, the alarm is inactive. I don't think I have this active, but just in case I do, get ready for a loud noise. When you separate them, all right, good. The alarm goes off. I'm going to put these together, and I am going to arm this. I'm going to take it away. If anyone is not down with loud noises, cover your ears. In 3, 2, 1. And I just unlocked it. That's the alarm. Here's the kind of fun that we can have with this alarm. This is the fob controller that activates and deactivates the alarm. It arms and disarms. It is a lot of fun working with this stuff. So I'm going to stop this. I'm going to go back to RTL SVR. Now, if I key this, wasn't supposed to do that, sorry. It should give you some kind of a signal. This is the disarm. Now, just by virtue of doing some searching, I figured out where this signal was. And if I could remember, then this would be fantastic. But don't worry, if I can't remember, I got a video of it because I'm awesome like that. Well, if that fails, the other standard is about 315 megahertz. Strange, weird, can't find it. Remember when I said this is not an exact science? Sometimes stuff like this will happen. Something might be interfering where I can't pick it up. Oh, there it is. There we go, we got it. All right, crisis averted. Way to go, Gray Fox. So there's my signal. It's at 433.9, something like that. Now that I know that signal, the next thing that I would do is try to demodulate the signal, try to figure it out. Now, the troubleshooting that I did was nice and fantastic. I could have did some research and actually found what was going on with this alarm. The problem is that when I opened it up, I found nothing. No FCC ID, nothing like that. So this I had to do by hand, exactly what you just saw. That's probably 20 hours of my day is doing stuff like that. Just doing some general research, finding where stuff like this would operate in the general sense, and then going and troubleshooting. And that's basically what you do. When I cracked this open, I found nothing that told me any frequency, so I had to go and I had to do it manually. So that's what you have to work with sometimes, and that's why this was so much fun. So we're going to signal replay it. A signal replay is essentially where you take the signal, you copy it, you replay it. I'm going to use a flipper 0 to do this. Here is my flipper 0. So you go to start, and the cool thing about this, it's a jack of all trades. You go to Sub-GHz, and you can read essentially anything that you want to. So I'm going to go here, and now I can read raw, I could do save stuff. If I read raw, it just gives me one of these. Now I'm going to hit record. Let's do the unlock signal. There it is. Now I'm going to stop this. Bam. And now I can save it, or I can send it. I am not pushing any single button here. Come on, man, you can do this. Let me save it and see if that makes a difference. Save, that's fine. All right. Go back, go to saved. Let's play this. I'm gonna try it one more time. I don't know, this never happens. All right, let's read raw. Gonna record this, unlock, stop, send. Interesting. All right, well, that's demo failure number 1. But I think you guys all get the idea. You saw that I recorded a signal. This repeats, and then it should give you the same kind of signal back. The reason why it's not playing, I'm not sure. It might be the proximity of some other signal. It could also be that I had the fob right there. But yeah, weird. Anyway, that's failure number 1, and I apologize for that, but that's okay. We're going to press on. But you saw how that works. You saw how I did that. The principle is the same. And you can do a DDoS attack using the same principles. Now, you saw how I did a copy and how I did like a repeat. It didn't work on this one, but it could work on other ones. Another way to do this is not copying a signal, but just trying to deny the signal. Now, the way you do that is you have a signal, something like this remote that's putting out that alarm signal. If I can't copy it and replay it, then I can make sure that nobody can play it ever again. I know the frequency this operates on, so I can generate that signal and I can drown it out. The way to explain a DOS attack with radio is the same thing as like someone is having a conversation and you walk right up to them, you go, ah, la, 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 la. Nobody can hear what they're saying. You just DOS them. That's how that works. Now, I'm kind of hoping this demo also works. We'll see what happens, but here we go. Now I have SDR Sharp, and I have SDR Angel up. SDR Angel is connected to my hack RF. This can generate a signal, whereas the RTL SDR only receives a signal. I know what the frequency is here. I'm going to key this again. And you see that signal went up. So if I start my hack RF and I start generating a signal, I can take this signal down right where I need it. And you can see the peak is there. And I moved it, excuse me, just about where I need it. Let's zoom in a little bit. All right. So you can see over here, that's the signal I'm generating right there, that big peak. Now do this unlock again. All right? Now let me move the signal closer in where it's just above this signal. All right? Now let's amplify it, give it some more oomph, give it some more juice. And now widen it a little bit. You can see the signal is still going, but this is not reading it. It's being drowned out by the hack RF. This demo worked. Nailed it. You can do the same thing with all kinds of other RF, and this is why I had that disclaimer. That disclaimer definitely means something. You want to make sure you're not doing something illegal, because if you DOS, you denial of service, something that people depend on, like the electrical grid or water or a vehicle, it can be hairy for you. This video is me demoing this same thing with a car fob. Unfortunately, I don't have any sound. If you did have sound, then you would hear that the car is actually going beep when I do this. Now I start the signal with the hack RF, and I'm going to amplify it, and I'm going to widen it a little bit so I can try to drown out that signal. Now I got a big signal, and now you see lights aren't going on, nothing is happening. I drowned out that signal. It'd be cooler if you had the audio so you could hear the beeps, but just seeing the lights not activate, that's enough to demonstrate that this DOS attack worked on that particular vehicle. So, let's go to the next slide because we already saw this. Okay, now that we went over that, here's some more ideas, things I'm not able to demo simply because there's not enough time or I just don't want to get arrested. You can get a tiny SA Ultra spectrum analyzer, which is a really cool little handheld thing that can analyze the spectrum in a really wide view, and it'll give you that waterfall that I'm talking about. So with just one antenna that can cover a whole bunch of RF, you could see exactly what's going on in your environment in something like 100 megahertz worth of bandwidth, or maybe a gigahertz of bandwidth. Obviously, the more wide you get, the less accurate you are, but it gives you something to start. Next thing you can do is radio direction finding. There's an SDR called Kraken SDR. It's called Kraken SDR because it has I think it's 6, it could be 8 different antenna outputs that you can attach. Each antenna gives you a little bit of an offset of how you're going to detect your RF. That offset will allow you to triangulate signals. So if I have an antenna here, an antenna there, and somebody keys over there, this will get a stronger signal, this will get a weaker signal. Let me reorient this way. Somebody keys over there, same signal, great. Now we can triangulate and we can at least get somewhat of a defined area of where that signal is. And that's how you direction find. You can use a Blade RF and you can start your own cellular phone service thing. Stingrays do that already, but they only do it on 2G. I hate to tell you guys, but there's new technology that allows those who can afford it, whether it's government or not, to be able to simulate cell towers that are also 3G, sometimes LTE, but I have no documentation on that, probably because it's super classified. But if you use a Blade RF and you happen to work in the 5G, LTE, or even the 3G UMTS space, you can simulate a cell tower and you can start doing experiments and pen testing. It's about the same price point as a hack RF. And then you can do GPS signal spoofing, and you can use a lot of things for this, but I've only ever done it with a hack RF or a Lime SDR. You can get on GitHub and you can get a GPS simulator. You can spoof GPS signals from a hack RF. I can do this on the side of a highway. Your in-laws are coming to visit. You don't want them to find you. They have their GPS on. They know they're heading to Pittsburgh, but as soon as they reach 376, suddenly their GPS says they're in Thailand. You might buy yourself some time. I'm not advocating for this, I'm just saying it's applied. Preparation of the battle space, remember? let's see how much time we have left. Not a lot. But I can't demo Wi-Fi, but Wi-Fi is everywhere. And you can use a Flipper Zero and probably some of this other equipment to do a Wi-Fi deauth attack. And the way that you would do that would be using this guy. So if you have a Wi-Fi dev board on your GPIO, which is the top of your Flipper Zero, you could put like different boards in these chips and it'll give you some expanded capabilities. I was using a Wi-Fi dev board. This can do natively RF, IR, like RFID, infrared, sub-GHz stuff. It can't do Wi-Fi natively, so you got to put in your own board. Using that, I detected all the beacon packets of SSIDs that were around me. I listed them. I found my target. And then after I found my target, I went and I started putting out deauth packets. For those of you not familiar how to hack Wi-Fi, the way Wi-Fi talks to each other is you're authenticated to a network. It goes by packets in the air. If you inject packets that say deauthenticate that user, it'll deauthenticate. And if that user auto connects back, then you can collect those new authentication packets which has the password in it. And that's how you would crack a Wi-Fi password. And that's what I did here. My attack is going to be deauth. Now I'm running it, and now I'm going to go down here. I'm going to sniff all the raw packets. Now that I'm sending deauth, I am now sniffing those packets. And then if all goes correctly, after you're finished collecting stuff, you stop it, and then you save that file. This is me collecting all those packets, including the deauthentication and reauthentication packets. If I'm lucky, I'm going to get packets that are going to be EA-POL packets, otherwise known as reauthentication packets. It's going to be your Wi-Fi four-way handshake. It's going to have passwords in it, probably encrypted, but that's why we do password cracking. And so now I saved it. Saving it, I can open it up with some kind of a packet analyzer, which for me is going to be Wireshark. And then there you go. I went and I did a search for EA-POL packets, and I was able to find them. Did I do that search? I don't know. I don't think I recorded that part. But if you filter for EA-POL, which is extensible authentication something, you smart people probably know what it is. I work in layer 1, man. But those are packets that are going to have the passwords. And then from there, you would crack it. But that's beyond our scope, unfortunately. So let's do it anyway. Here we are. This is me in Linux, Kali Linux, and I'm doing run-of-the-mill aircrack NG stuff just like anyone else does. I'm selecting my packets, and then I'm going to go through, and I'm going to brute force it, and I'm going to get what I need to get. This video is going to play out, and then the next slide is just going to be questions. So while this is playing out, any questions? Yes? I'm sorry, but the war hath taken my hearing.
All right, here we go.
From what you showed me, would it be possible to identify and recognize air-gapped computers and servers and disrupt them from these signals?
That's complicated. You could do that. So the question basically is you have an air-gapped computer that has no network connectivity. Can you use software-defined radio to detect it? The answer is yes, but it's not going to give you what you think it's going to give you. So air-gapped computers need to run, so they're going to have power cords, power cables. You're going to have resonant frequencies from the power cables. If you get really deep into like things like Van Eck freaking, where you pick up signals from an LED monitor and you reproduce the picture from the pixelation sequence, you can do that, but unfortunately, none of that really has the intelligence value that you might need. So if you're looking for something that will, if you're looking for content, stuff like that, SDR is not going to get you what you need. You're going to need to have physical access to that air-gapped computer in order to either put a transmitter on it or to have something so close to it that you can maybe pick up data that's going through like unshielded twisted pair, Ethernet, something like that. Does that answer your question? All right. Anyone else?
Hey, thank you. So there's like some dude who tracks people's airplanes on Twitter, like Taylor Swift and Elon Musk, and then he puts out where their aircraft is. Do you know if he's doing that using some of these public repositories of ADSB channels, or is he using his own, or is there some other way?
Yeah, that's probably part of it. The thing is, there are many ways that you can detect trajectories, locations of aircraft. ADS-B is one of them, but it's not the end-all be-all. It's just one component. You can also have more sophisticated equipment that can actually get the official transponders of these aircraft. You might also have other means that are not software-defined radio, but are actually like network taps that can get into that maybe have access to servers that have these data, and then from there you can enrich whatever program that you want. But if you're doing it specifically just with software-defined radio, commercial off-the-shelf stuff, ADS-B is more than likely 75% of what they're getting, and then the other 25% is going to be actual transponders, like real FAA transponder frequencies, which are typically not advertised because they're meant to be sensitive government communications. I may be wrong on that one, but it's not something that's well advertised, whereas ADS-B is just out there in the open. The problem is you're not required to transmit ADS-B signals. You are required to transmit transponder frequencies. So you may get what you want, you may not get what you want, but for the most part, a lot of that is going to come from something like ADS-B. Answer your question? All right, cool. Who else?
Talk loud and hold it close.
Yep.
Yes?
I got a question about the car fob.
Yeah.
Right. So you did basically a masking of the car fob unlocking a car, right, by a larger band. Now, does that mean, let's say I'm that driver, and I press it 3-4 times, I'm like, the battery's dead or something, I stop. Can you now replay that first capture?
Yeah.
Because you blocked it?
I'm really glad you asked that. That was going to be something I wanted to demo, but it probably would have taken up a lot of time. You can jam that kind of a signal so that the user of the key fob cannot activate or deactivate the car or interact with it one way or another. But you saw that the signal was still being played, even though I was jamming it. You could record that, and then you can get a band filter or some other kind of digital filter where you take out the raw signal that I was playing, and now you have that original signal. Another way to do it, and I was too low a power to do this, but you offset the jamming signal by a few hertz so that you have the concurrent signals. They're next to each other. They're not interfering with each other, but this one is still so loud that it's still within the band pass of the original signal, so it'll still block it. But now I have an unfettered recording of that. And that's actually the way that works. You jam it so someone's not able to get to the car, and then they walk away to try to call somebody or whatever. Now that I recorded these, but they are not recorded in the vehicle security system, I can successfully replay them. Remember that disclaimer. All right. Anyone else?
Yeah, I have a question. Appreciate the warning on, do this to your own equipment. Is there anything that is cloud connected or anything like that you have to be careful? Like even though you're doing the local signal that, might get detected and picked up by those service providers?
The VA loves me because my hearing is crap. So I'm going to come over to you, and can you please repeat that?
So when you're hacking...
That was another free demo of a DOS. Go ahead.
All right, let's try this one more time. So when you're going after your own equipment, is there anything that you need to be careful of when the equipment is like cloud connected, that they can tell, even though it's a local signal that you're interfering with, but they get some sort of feedback?
No. If I'm understanding you right, you have equipment that's connected, but it is also being cloud backed up, or it has another connection. Everything we're doing is layer one. It's all going to be in the immediate RF environment. So if it's connected over the internet to something, then there should be zero interference unless, your cloud server or wherever was on-prem next door. Then you might have somebody knocking down your door. But yeah, you should be fine. Got a radius with this guy. All right, anybody else?
What was your most interesting thing that you've seen that gave off a frequency that surprised you?
Most interesting thing. Okay. Well, there's a lot. I'll give you the most recent interesting thing. When I was designing this presentation in my home lab, I had this very cable that's connecting my laptop to the audio visual. It's a DisplayPort to HDMI converting cable. at particular frequencies with that same Baofeng radio, specifically at about 146 and 147 megahertz, if I was within 3 feet of it, I would key it and it would kill it. It would kill the cord. My monitor would just go blank and it would reset. I'd back up a foot, do it again, nothing. Go forward a foot, do it again, kill the monitor. Go forward another foot, do it again, kill the monitor. I went up a few megahertz, same thing. Went up a few more megahertz, nothing. So that to me means that this cable is resonant in some frequency that can gain interference from a strong radio signal. And that to me is really, really interesting because, once again, that disclaimer, if you get something that's strong enough, you may be able to disrupt an entire organization's wires everywhere. You could black monitors out, you can black electrical cables out, IoT, anything that happens to like have either a really crappily designed cable or a crappily designed monitor, you can DOS all that stuff. I think that's super, super interesting because it happens instantaneously, and if you try to analyze it, it's already too late. You have no monitor, so how are you gonna analyze it anyway? All right, I'm pretty sure that I'm out of time by now, but if anyone wants to catch me offline, you can, I'll be around. Anyone else? Okay, one more.
Whenever you were preparing your battle space, how often was it that you encountered signals you couldn't identify, and how did you deal with those?
The middle of the question, can you repeat that?
How often did you encounter signals that you couldn't identify?
Gotcha.
And how did you deal with those?
All the time, every time. Most typically, we would have documentation from, some precedent source, like other surveys that, people may have done, or things that we get from open source or even classified material that would tell us what signals were being put out by what. We know that there are cell towers in the area. We know that there are radio towers. There's VHF, UHF repeaters, DMR radio repeaters. The APCs and tanks that these units are using communicate over this frequency for their command and control. We would know a lot of that, and the majority of our job was listening to make sure that that was right. And if we didn't hear any of that, then we would go searching around it to see if we could find it, if they changed it. If we're going into an area that just has raw signals everywhere, and we have no prior intelligence from any documentation or any other intelligence source on the ground, then it could take 2 weeks, 3 weeks, maybe a month, even a year, depending on where we are, to get a real good idea of like what the baseline noise floor is and what those frequencies are, what they go to, how to attribute them. It also depends on like the kind of target. If we got a call that somebody somewhere is going to do something bad, it's going to be kinetic and people are going to get hurt, sometimes we don't care about the RF. We'll go to human intelligence or some other intelligence, and we just won't listen on signals because we just don't have the time. But if it's something where we can take our time, we can survey an area, and we need to go in here and we can't put people in there because it's a non-permissive area, then we'll sit there and we'll analyze those signals as much as we can. And I would probably say 50% of the time we can't attribute a signal. And if we can't attribute it, there's nothing we can do about that. Sometimes you got to stop admiring the problem and you got to move on. Other times you can make definite sure what you're seeing is what you're seeing. If you have a UAV flying over a particular truck and you keep getting CB radio coming off of it and it co-locates with that truck, it's probably that truck. All right, I'm not going to spend any more time on that. Let's do it. Let's move on. Don't let perfect be the enemy of good when it comes to RF because you're just going to tear your hair out. Does that make sense? All right.
All right, the legendary Gray Fox, everyone. All right, we're going to start our next talk in about 10 minutes. Going to take a break and come on back. I hear the cookie table's out.